Hey everybody, it's Mr. Mott. What we're going to do is go through the calculations for our finding the equilibrium constant lab. This is our equilibrium system that we eventually set up to form the Fe SCN 2 plus complex. And so if we want to find the equilibrium constant, what we need to know is the concentrations at equilibrium. So normally what we would do is set up we'd have our reaction, and then we'd set up an ice table. Okay. First thing that we would look at is what are our concentrations at the beginning, our initial concentrations. Initially, we don't have any of our complex, but we can figure out how much of our iron and thiocyanate concentrations are. All right. So for this particular solution that we used 3 milliliters of a 0.002 molar iron solution. We mix that with 2 milliliters of a 0.002 molar thiocyanate solution, and then we also added 5 milliliters of water. Okay, the water is important so we know what our total volume is. So what we can do is use our molarity equals moles over liters, rearrange that. We can figure out moles by multiplying the volume in liters, in this case it would be 0.003 liters, and multiply that by our molarity. And we can do that for both of these. All right. So multiplying by 0.003 liters times my molarity, we get a number of moles as 6 times 10 to the minus 6 moles of our iron 3 plus. When we do a similar thing for our thiocyanate, this is going to be 0.002 liters. Multiply that by the molarity, and we get 4 times 10 to the minus 6 moles of the thiocyanate. So that's how many moles we had. And then what we can do is divide that by our total volume, which is 10 milliliters or 0.010 liters. Okay. And then that's going to give us the molarity for each of these. So the molarity of the iron 3 plus is going to be 6 times 10 to the minus 4th molar. And then for the SCN minus is going to be 4 times 10 to the minus 4 molar. And then what we can do then is put that in for our initial concentrations here. All right. So that's what I'm going to go ahead and write in here. So 6 times 10 to the minus 4th molar for iron, and 4 times 10 to the minus 4th for the thiocyanate. And again, 0 for our initial concentration of our complex. All right. Now, so what we did in our lab is we had created a calibration curve, and then we read the absorbance of our equilibrium system. So when we mixed these solutions together with our water, we let the reaction come to equilibrium. We read the absorbance, and then we're going to use the information from our calibration curve. All right. So the calibration curve, I don't have a picture of it, but we don't necessarily need it, was absorbance versus concentration. And you would have a straight line here, and we'd have the lab quest give us our slope and our y-intercept, and we'd also read the absorbance of our unknown. So for this particular set of data, the slope was 3344.1. The y-intercept was 0.0035625, and the absorbance of that equilibrium system was 0.092. Normally we could kind of interpolate along the line, but the concentrations are really low, and so the LabQuest can't read out to more than, say, 3 decimal places. So we couldn't interpolate. We have to use our slope formula. All right. So our slope formula is y equals mx plus b. And then And so we're going to sub in our absorbance here. If you think about that, that's on our y-axis. We have our slope and we have our y-intercept that we'll plug in as well. What's on the x-axis, that's concentration, which is what we're going to try to find out. So let's plug in my absorbance of 0.092, slope of 3344.1 times x, plus 0.0035625. And then solving for x is going to be 2.64 times 10 to the minus fifth. And that's our concentration at equilibrium of our equilibrium system. So it's going to be this value here that we plug into our concentration at equilibrium in our ice table. All right, so that's going to go here. All right, let's see if I can paste that. All right, so that is our concentration at equilibrium here. Now, why is that important? Well, what we can then do is that we know that if we start out with 0, and then this is what we have at equilibrium, we know our change is basically a positive version of this. All right? And then it also tells us then that stoichiometrically everything's in a 1-to-1 ratio. So if I had a positive change, so let's go ahead and write that in there, a positive change of 2.64 times 10 to the minus fifth, then we have a negative change of that same value on our reactant side. So negative 2.64 times 10 to the minus 5, negative 2 or minus, I should say, 2.64 times 10 to the minus 5. And then when we do our subtraction here, we are going to get, for our equilibrium concentration for the iron, is going to be 5.74 times 10 to the minus 4, 3.74 times 10 to the minus 4 for the thiocyanate. And then now that we have these values at equilibrium, we can plug them into our equilibrium expression. All right. So just so I can have a kind of a newer, clean place to work, let's copy that, and then we're going to repaste it down here. Okay. And so now our Kc expression, or KEQ, would be concentration of our Fe SCN 2+ complex over the iron times the thiocyanate. And now we're going to plug in our values at equilibrium, which we just found out. So we have 2.64 times 10 to the minus 5. That's going to be over 5.74 times 10 to the minus 4. 3.74 times 10 to the minus 4 here. And when we do our math here, we should come up with roughly 123 for our Kc or KEQ. And that turns out to be really, really close to what the actual or accepted value is. At 25 degrees, which is roughly what we were at in our room, the accepted value is 138. So the value that we came up with is super similar, I think, to what the accepted value is. And that's pretty amazing for a high school lab, I think. So well done. All right. Hopefully that helps, and thanks for watching.